What if you could construct an exact polynomial from just a few points? And what if every polynomial had fundamental building blocks? Let's explore how. Polynomials exist as highly rigid structural objects within a vector space over a field. This exploration relies on the rigorous academic framework established by Kenneth Hoffman and Ray Kunze in their classic text, Linear Algebra. We begin with construction, using Lagrange Interpolation to build a specific polynomial from raw data points. Next, we analyze grouping, examining how polynomials organize into algebraic structures known as ideals. Finally, we perform a microscopic dissection, breaking these polynomials down into their irreducible prime components. Mastering these three phases allows us to define the precise structural behavior of any polynomial function. To solve the interpolation problem, we must find a unique polynomial of degree n or less that passes exactly through n+1 distinct elements in a field. The mechanical solution is the Lagrange basis polynomial, Pix. The numerator deliberately omits the x minus ti term. This omission ensures the entire expression evaluates to 0 at every other data point, tj. The denominator acts as a scaling factor. It normalizes the expression so that when x equals ti, the result is exactly 1. This creates the Kronecker delta property. Effectively, each basis polynomial functions as an independent mathematical switch. These n+1 polynomials are linearly independent, meaning they form a basis for the subspace of polynomials with a degree of n or less. The resulting polynomial f is the sum of each target value ci multiplied by its corresponding basis polynomial. Consider a degree 2 example using 3 arbitrary points, t0, t1, and t2. If we input t0, the p1 and p2 terms become 0. This isolates c0, p0, which equals our target value, c0. This zeroing out behavior repeats for t1 and t2, isolating c1 and c2 respectively, without interference from the rest of the set. Lagrange interpolation provides a deterministic structural guarantee of a polynomial's exact path through every specified point. Beyond individual construction, we must examine how infinite sets of polynomials group together within the algebra f of x. We define these groups as ideals, subspaces that are closed under both addition and scalar multiplication. An ideal is defined by its absorption property. If you take a polynomial g from inside the ideal and multiply it by any polynomial f from the broader algebra, the product remains inside the ideal. When an ideal is generated entirely by the multiples of one single polynomial, it is called a principal ideal. According to Theorem 7 in the Hoffman and Kunze text, every non-zero ideal in this algebra is a principal ideal. This means no matter how complex the collection of polynomials appears, there is always a unique monic polynomial of minimal degree that generates the entire set. Example 7 illustrates this reduction. Here, the ideal m is defined as the sum of multiples of x plus 2 and x squared plus 8x plus 16. Through algebraic reduction, we can subtract a specific multiple of the x plus 2 generator from the quadratic generator. This linear combination causes the variable terms to cancel out, leaving the scalar 1 as a member of the ideal. Because 1 absorbs all multiplication, its presence means the ideal automatically contains every possible polynomial in the algebra f of x. These two generators are relatively prime, and their collective behavior is ultimately governed by that single minimal generator. If single polynomials generate entire ideals, we must determine what dictates the internal structure of those polynomials. This depends on whether a polynomial is reducible, meaning it can be factored, or irreducible, which we call prime. The unique factorization theorem states that every non-scalar monic polynomial can be expressed as a product of monic primes. Much like integers, polynomials over a field possess a unique set of prime factors that cannot be altered without changing the polynomial itself. However, primality is not an inherent property of the equation. It is strictly defined by the scalar field f in which we are working. Consider x squared plus 1. Its atomic structure changes depending on our choice of field. Over the field of real numbers, x squared plus 1 is irreducible. No real number squared can result in -1, so no real roots exist to break the polynomial apart. Shifting to the field of complex numbers changes the structural limits of the system. In this field, the polynomial becomes reducible. factoring into the distinct linear components x plus I and x minus I. A polynomial's prime factorization acts as its fundamental structural blueprint, dictating its behavior within a specific mathematical environment. We can now view the architectural framework of polynomial vector spaces through these three established pillars. First, interpolation provides the method for building a polynomial to fit any specific dataset. Second, ideals define how these polynomials group together, reduced always to a single generator. Third, factorization bisects those generators into their irreducible, field-dependent components. These three tools establish the specific rules for constructing, organizing, and decomposing polynomial functions within linear algebra. If you found this helpful, like the video and subscribe for more clear explanations from Hoffman and Kunze linear algebra.